Good morning, champs. In this video, we introduce one of the most important models in fluid mechanics, potential flow. Potential flow is an idealized description of fluid motion. It is based on two assumptions. First, the flow is incompressible. Second, the flow is irrotational. Incompressible flow means that fluid does not locally expand or compress. Mathematically, this means the divergence of the velocity field is zero. In simple terms, the amount of fluid entering a small volume is equal to the amount leaving it. The second assumption is that the flow is irrotational. This means that the curl of the velocity field is zero. Physically, this means fluid elements do not experience local spinning or rotation. A very important mathematical result follows from this condition. If the curl of a velocity field is zero, the velocity can be written as the gradient of a scalar function. We call this scalar function the velocity potential, which we denote by phi. So the velocity vector can be obtained by taking the gradient of phi. In Cartesian coordinates, this means the x velocity component equals the derivative of phi with respect to x. The y velocity component equals the derivative of phi with respect to y. And the z velocity component equals the derivative of phi with respect to z. The divergence of the velocity must be zero. Since the velocity is the gradient of phi, the divergence of the gradient of phi must be zero. This leads to Laplace's equation. Laplace's equation is the central equation of potential flow. It tells us that the second spatial derivatives of the potential must balance in such a way that their sum is zero. One important property of Laplace's equation is that it is linear. This means if two functions satisfy the equation, their sum also satisfies it. Because of this property, we can build complex flows by adding together simpler solutions. This idea is called superposition, and it is extremely important in potential flow theory. Now let us introduce another useful quantity called the stream function. For two-dimensional flow in the xy plane, we define a scalar function called psi. The x velocity component is defined as the derivative of psi with respect to y. The y velocity component is defined as minus the derivative of psi with respect to x. With this definition, the continuity equation is automatically satisfied. The stream function also has a very important physical meaning. Curves where psi is constant represent streamlines. A streamline is a curve that is everywhere tangent to the velocity field. Later, we will use this property to represent the contour of bodies in potential flow problems. In two-dimensional potential flow, we therefore have two scalar functions, the velocity potential phi and the stream function psi. These two functions are related to each other through special mathematical relations that connect their derivatives. Because of this connection, we can combine them into a single complex function. This function is called the complex potential. The real part of this function represents the velocity potential, and the imaginary part represents the stream function. Let us finish with a very simple example. Consider a uniform flow moving in the positive x direction with constant velocity u. In this case, the x velocity component is u and the y velocity component is 0. From the definition of the velocity potential, we obtain that phi equals u times x. From the definition of the stream function, we obtain that psi equals u times y. The streamlines are therefore given by constant values of psi, which correspond to horizontal lines. This matches exactly what we expect for uniform flow moving in the x direction. To summarize, potential flow assumes incompressible and irrotational motion. This allows us to introduce the velocity potential, which satisfies Laplace's equation. In two-dimensional flow, we can also define the stream function, whose constant values represent streamlines.